In this section, we will learn about the methods to prepare haloalkanes. In chapter number 6, we learn that alkenes can be a source from which haloalkanes can be prepared. For example, an alkene, when it reacts with halogen acid, it gives rise to uh, haloalkanes. This is an example of addition reaction in which halogen acid add to the double bond, and this addition is a Markovnikov's addition. Although it's a good method to prepare haloalkanes, however, many simple and low molecular weight haloalkanes are prepared by halogenation of alkanes. Previously, we learned that alkanes are not very reactive molecules and they do not undergo many reactions. However, under special or certain conditions, alkanes undergo reactions with halogens to give rise to haloalkanes. So let's learn about these reactions. Halogenation of alkanes is common with bromine and chlorine. Fluorine is rarely used because its reaction with alkanes is extremely exothermic and it may even cause explosions. Iodine is also very rarely used because its reaction with alkanes is endothermic and the position of equilibrium favors the reactants rather than the products. In chapter number 2, we learned that alkanes are uh, not very reactive hydrocarbons. So if we keep a mixture of an alkane such as methane and chlorine under normal circumstances, nothing will happen. So no reaction will take place. However, if this mixture is heated or it is exposed to visible or ultraviolet light, a reaction begins at once, and this reaction is exothermic reaction, and we will see evolution of heat. The product of this reaction is chloromethane and hydrochloric acid. This kind of reaction is known as a substitution reaction. A substitution reaction is a reaction in which an atom or group of atoms is replaced by another atom or group of atoms. For example, in this case, one of hydrogen atom is replaced by chlorine atom. So that's why this reaction is known as a substitution reaction. So the reaction of chlorine with an alkane such as methane, as we saw in previous slide, will give us a substituted product in which chlorine atom will replace one of the hydrogen atom bonded to a carbon, and the product will be a chloroalkane. In this particular example, our product is a chloromethane. This reaction is known as chlorination reaction. If the product obtained in this reaction is allowed to react further with more chlorine, we will get a dye-substituted product. For example, chloromethane can react with another molecule of chlorine, and the end product will be a dye-substituted uh, product in which there are two chlorine atoms connected to the carbon atom. So the end product in this reaction is a dichloromethane. If we have large quantities of halogen, such as large quantities of chlorine gas available in this reaction, then the product will further react with chlorine and we will get a tri-substituted and eventually a tetra-substituted methane. So therefore we can write those reactions as shown here. So dichloromethane will react with another molecule of chlorine and our product will be a trichloromethane. Trichloromethane is also known as chloroform, and if we have more chlorine available to react, then the trichloromethane will undergo one more substitution, and we will get a tetrachloromethane. So what can we say about this reaction? So if we use 1:1 mixture, then the reaction will stop at first step and our product will be a uh, chloromethane. However, if we use excess of chlorine, the chloromethane product will continue to react until we reach the fully substituted product, which is tetrachloromethane. In this chlorination reaction, it is possible to prepare a chloromethane as shown here by using 1:1 reactant composition, or we can prepare the tetrachloromethane. In that case, we have to use excess of chlorine. However, it is not possible to stop the reactions at the dichloro stage or trichloro stage. In that case, we will get a mixture of all three possible products. So either this reaction is good for the mono substitution or fully substitution. The middle two steps are not very convenient, so it's not possible to stop at the dichloro step or trichloro step. The regioselectivity is quite high for bromination reaction, but it is not as high for chlorination reaction. For example, the reaction between bromine and propane gives 92% 2-bromopropane and only 8% 1-bromopropane. If you look closely, you will find that the major product, which is 2-bromopropane, is a secondary alkyl halide. On the other hand, the minor product is a primary alkyl halide. We will come back to it in a little while. Just remember that in case of bromination, the secondary alkyl halide is the major product over the primary. However, in case of chlorination of propane, uh, there is not that regioselectivity. For example, 57% is the secondary alkyl halide product and the primary alkyl halide product is 43%. There is a slight preference for the secondary product, but not as high as bromination. The regioselectivity of halogenation reactions follows this order, according to which the tertiary product is preferred over the secondary and secondary is preferred over the primary. For bromination reaction, the ratio between tertiary, secondary, and primary is 1600:80:1. So what does that mean? That means is for every one primary bromination product, we will have 80 secondary bromination product and we will have 1600 tertiary product. So in other words, if in a molecule there is a chance that both primary, secondary, and tertiary product can be obtained, for every single primary product we will obtain 1600 tertiary products. So that tells us how greater is the preference for the tertiary product. However, in case of chlorination reaction, this ratio is roughly 5:4:1. So in other words, for every one primary chlorination product, we only get 5 tertiary chlorination product. And between the secondary and tertiary, the preference is is almost similar. For every 4 secondary products, we will get 5 tertiary products. So secondary and tertiary in chlorination have almost the same preference. Slightly high preference for tertiary, but not as high as in case of bromination. Let's solve this problem based on the bromination reaction. So in this case, we need to find the percentage of all the products obtained in this reaction. So if we look carefully, the only possible products are the tertiary product and secondary product. That is because uh, all methyl groups are equivalent, so they are all gonna give us a primary alkyl halide, and the remaining CH, so the replacement of this one will give us a tertiary. So only two products are possible. So either we will get uh, tertiary bromo product, or we will get a primary bromo product. We need to find the percentage of both of them. We know that the percentage follows, or the ratio follows this um, rule. So for every one primary, we have 1600 tertiary products. So in this case, we have 9 primary hydrogens. So 3 here, 3 here, and 3 here. So total 9 primary hydrogens and only 1 tertiary hydrogen. So therefore, if we calculate the percentage, so the percentage of tertiary product will be equals to 1 times 1600. So that's the because we have only one tertiary and the preference is 1600 times for tertiary, divided by the total number of hydrogens and total preferences. So it would be 1 times 1600. There is no secondary, so therefore it would be 0 times 80 plus 9 times 1. And if we solve all that and multiply it by 100, me multiplied by 100 to calculate the percentage. So if you solve this equation, we will get the percentage comes out to be 99.4%. So in other words, in this reaction, 99.4% will be the tertiary product and only 0.6% will be the primary product. We can learn a lot about halogenation reactions by careful consideration of the energetics of each step. In energetics, we look at the energy required to break a bond, which is known as bond dissociation enthalpy or bond dissociation energy. Bond dissociation energy is defined as the energy required to break a covalent bond homolytically in gaseous phase. So for example, if you want to calculate the bond dissociation enthalpy of C and H bond, it is measured as the energy required to break this bond homolytically. Homolytically means that after breaking the bond, one of the electron will go to one atom, the other electron will go to the other atom. So this is known as homolytic cleavage. The bond dissociation enthalpies of various carbon-hydrogen bonds are given in this table. If you compare the values of bond dissociation enthalpies of methyl, so this one is methyl, so methyl has the dissociation enthalpy of 439 kilojoules per mole. That's for methyl. And the carbon hydrogen bond in a primary position, so which is this case, so that's a primary, and the bond in dissociation enthalpy is 421. And for secondary carbon hydrogen bond, that's the secondary, and the bond dissociation enthalpy is 414. And finally, the tertiary bond dissociation enthalpy, carbon hydrogen bond, is 405, secondary and tertiary. So as you can see that more energy is required to break a carbon hydrogen primary bond and less energy is required to break a carbon hydrogen tertiary bond. So why would that be? So the reason is that after the dissociation or after the cleavage, the product in tertiary is more stable. So because the product is more stable, hence less energy is required to break that bond. So what can we say here? So therefore we can say that the methyl radical, which is the product of dissociation of primary carbon, so that's the product, is less stable, and the product of tertiary is a tertiary radical. So these are called radicals because they have one free electrons. So these species are known as radicals. They are not carbocations, they are not carbon anions, they are called carbon free radical or carbon radical, not the hydrogen, of course. And this is a carbon radical. Similarly, this is a methyl radical. And in case of tertiary, the product will be a tertiary carbon radical. So the stability order is tertiary radical is more stable than secondary, secondary is more stable than primary. Doesn't it look similar to carbocation order? So in carbocation also tertiary was more stable than secondary, and then primary was the least stable. And of course methyl is also the least stable. So the carbon radicals follow the same stability order as uh, uh, carbocations. It makes sense. In carbocations, carbon which has a charge has less than octet or less than 8 electrons, and in radicals also it has less than 8 electrons. So in both carbocations and in carbon radicals, the charge carrying or the radical carrying species is electron deficient, and because of that they have similar stability orders. Now, because tertiary radicals are more stable, so therefore they will be more readily formed, and because they will be more readily formed, therefore the tertiary substituted product will be the major product. So hence, by just looking at the energetics or the bond dissociation enthalpies, we can qualitatively explain why tertiary product is more preferred or is a major product. Chemists can also calculate the enthalpy change of any reaction by comparing the bond strengths in the reactants and products. The enthalpy change, which is also known as heat of reaction, is given by the total sum of bond dissociation energies of bonds being broken minus the sum of bond dissociation energies of bonds which will formed. For example, if we look at this reaction, in this reaction, we are breaking two bonds. So one bond is between carbon and hydrogen. So this bond will break, and other bond will be between chlorine and chlorine. So two bonds are being broken. Energy required to break the carbon hydrogen in methane is 439, and energy required to break the chlorine-chlorine bond is 247. Similarly, the new bonds which will form will be between carbon and chlorine and hydrogen and chlorine. And the bond dissociation energies are 351 for carbon chlorine and 431 for hydrogen and chlorine. So Therefore, the heat of this reaction, which is also known as enthalpy change of this reaction, is equals to the sum of all the energies which will break. So that's 439 plus 247 minus the sum of energies which will of bonds which will form. So that's carbon and chlorine, that's 351 plus 431. So if you calculate all these, the result will be negative 96 kilojoules per mole. And that's how chemists calculate the enthalpy of any reaction using the bond dissociation enthalpy values. From the detailed studies of conditions and products for halogenation of alkanes, scientists have concluded that these reactions occur by a special type of mechanism known as radical chain mechanism. Now, radicals are any chemical species that contain one or more unpaired electrons. Radicals are formed by homolytic bond cleavage, and as we saw earlier, homolytic bond cleavage means that in this uh, bond breaking step, one electron of covalent bond moves to one atom and the other electron from the covalent bond moves to the other atom. The order of stability of alkyl radical is same as carbocation order, that is tertiary alkyl radicals are most stable, followed by secondary and then primary, and methyl alkyl radicals are least stable. These reactions show the formation of radical. So in the first two cases, you will see that radicals are formed by homolytic cleavage of sigma bonds, and the sigma bond is surrounded by bunch of lone pairs. As you can see in case of the first example, the oxygen-oxygen sigma bond has 4 lone pairs around it. Now the repulsions between these lone pairs causes this sigma bond to weaken. So therefore energy required to break this already weakened bond is not that high. As you can see, the energy required to break or the bond dissociation enthalpy of this oxygen-oxygen bond is only 159 kilojoules. Similarly, the repulsions between the lone pairs of electron between two chlorine atoms also weaken this chlorine-chlorine sigma bond. Therefore, it can also undergo the homolytic cleavage easily. The energy required to break chlorine-chlorine bond is 247 kilojoule. Now, in case of carbon-carbon bond, there is no lone pair of electrons around this bond, so hence carbon-carbon bond dissociation requires significantly higher amount of energy. The energy required to break the sigma bond and generate radicals can be supplied either by heat, such as in case of diethyl peroxide, or it can also be supplied by light, such as in case of chlorine dissociation. The energy of visible and ultraviolet radiation falls in the range of 585 to 167 kilojoules per mole and is of the same order of magnitude as the bond dissociation enthalpies of hydrogen-halogen covalent bonds. On the other hand, peroxides and hydrogen or hydroperoxides have dissociation enthalpies in the range of 147 to 209 kilojoules, and compounds containing these bonds are cleaved by lower temperatures than those required to rupture carbon-carbon bonds. So now that we know what are radicals and how they are formed, let's learn about radical chain mechanism. This mechanism is observed in the halogenation reaction of alkanes. Radical chain mechanism has three characteristic steps. The first step is called chain initiation step. The characteristic feature of chain initiation step is the formation of radicals from non-radical compounds. In case of chlorination of an alkane, chain initiation is carried out by thermal or light induced hemolysis of chlorine bond. So as we can see in this first step, a homolysis of a chlorine molecule takes place, and this homolysis is carried out by either heat or light. The resulting product is a free radical or a radical. So therefore this step is known as chain initiation step, because in this step we will see that the chain of reaction will initiate. The second step of radical chain mechanism is chain propagation step. The characteristic feature of a chain propagation step is reaction of a radical and a molecule to give a new radical. For example, in case of chlorination of ethane, the first step, which was chain initiation step, resulted in formation of a chlorine radical. So in chain propagation step, this chlorine radical will react with a molecule, and that molecule is ethane molecule. The chlorine radical will cause a hemolysis in ethane molecule and will form a neutral molecule, which is HCl in this case, and another radical. And in case of ethane, this new radical is a ethyl radical. The ethyl radical will react with another chlorine molecule, resulting in hemolysis of chlorine, and the product will be a chloroethane and a new chlorine radical. This new chlorine radical will react with another ethane molecule, causing a formation of another ethyl free radical and a neutral molecule. So as you can see, that chain propagation step will continue for quite a while, because each step will create a new radical, and that new radical will cause a new reaction step, resulting in formation of a new radical. The number of times a cycle of chain propagation steps repeat is called a chain length. Chain lengths can range from few to many thousands depending on the relative rates of reaction and the concentration of various species. The final step of radical chain mechanism is chain termination. A characteristic feature of chain termination step is the destruction of radicals. The most important chain termination steps in halogenation of alkanes are shown in step 4 through 7. As you can see, in chain termination steps, radicals combine with each other to give neutral molecules, and hence the chain is terminated because radicals are no longer available. One of the important chain termination steps give rise to our desired chlorination product. However, the loss of ethyl and chlorine radicals terminate two chains and therefore stops many dozens to thousands of subsequent product forming propagation steps. We should note here that chain termination steps are usually rare compared to chain propagation steps. This is because at any given time the concentration of radical species is very low. making a collision between two radicals is relatively rare event. So it is hard for these radicals to find each other because their concentrations are so low and neutral molecules are more abundant. So the chances are that a radical will combine with a neutral molecule, resulting in a chain propagation step rather than chain termination. Chain terminations usually take place when most of the reactant species are already been converted to products and there are no more reactants available. At that time, the radicals will find each other and they will result in chain termination. Earlier, we learned about the regioselectivity of halogenation of alkane reactions. We learned that in halogenation reaction, the tertiary product is more favored over the secondary and secondary is more favored over the primary. Now, as we learned earlier that the regioselectivity of both chlorination and bromination can be accounted for in terms of the relative stability of alkyl radicals. We saw that the tertiary alkyl radicals are more stable than secondary, therefore the tertiary product is more likely to be formed. Hence, this explains the regioselectivity order. But then how do we account for the greater regioselectivity of bromination? How come in bromination the tertiary product over the primary is 1600 times more likely, whereas in chlorination the tertiary product is only 5 times more likely than the primary? How do we account for this such a big difference in bromination regioselectivity and chlorination? In order to explain this difference, we need to consider Hammond's postulate. It is a refinement of transition state theory proposed by George Hammond in 1955. According to Hammond's postulate, the structure of the transition state for an exothermic reaction step is reached quite early in the reaction. So for example, in this exothermic reaction, the transition state is shown here and this is the reactant. So from going from reactant to transition state, it doesn't take that much time. So therefore, in exothermic reaction, the transition state is quite close to the reactants. So therefore, the transition state resembles the reactant of that step more than the product. So in exothermic reaction, because transition state is closer to reactant, therefore it resembles more to the reactant. Conversely, the structure of the transition state for an endothermic reaction is reached relatively late. As we can see in this endothermic reaction, transition state is here and reactants are quite far away, so transition state reaches relatively late. However, in endothermic reaction, the transition state is more closer to product. So therefore, in endothermic reactions, transition state resembles more to the products rather than the reactants. It is important to note that it is not possible to observe the transition state directly. Until the advent of the modern computational theory, we could only infer its existence, structure, and stability from experiments. Hammond's postulate gives us a reasonable way of deducing something about the structure of transition state by examining things we can observe, such as the structure of reactants and products. Now let's apply Hammond's postulate to explain the relative regioselectivities of chlorination versus bromination of alkanes. The rate determining step in these halogenation reaction is the abstraction of proton by the chlorine free radical or the bromine free radical. The bond dissociation energies or the heat of reactions of this rate determining steps are given in this table. This table shows the enthalpy of 4 different reactions. In first reaction, uh, chlorine radical uh, abstracts a proton from the primary position, resulting in formation of a primary radical. In the second case, the chlorine radical takes a proton away from a tertiary uh, alkane, resulting in formation of a tertiary radical. Similarly, in reaction number 3 and 4, bromine radicals abstract protons from alkanes and resulting in formation of a primary free radical as well as tertiary free radicals, which are similar to the ones formed by chlorine reactions. The heat of these reactions are given, and these enthalpy changes were calculated by the bond dissociation energies as explained earlier in this chapter. The important thing to note here is that the enthalpy of reaction in chlorination is negative, so hence this reaction is um, exothermic. However, bromination, because it has a net positive heat change or enthalpy change, therefore bromination reaction is endothermic. So endothermic for bromination and reaction is exothermic for chlorination process. Now we learned that Hammond's postulate states that in case of exothermic reactions, the transition state resembles more like a reactant. So therefore, in chlorination reaction, the transition state resembles more like an alkane and not the product, which are radicals. So in other words, in chlorination reaction, the transition state has very little radical character. So if it has very little radical character, so the stability of radicals does not play any part in determining the outcome of the reaction product. So therefore, regioselectivity is only slightly influenced by radical stability. So in other words, in chlorination, the transition state resembles more like reactant. So reactants are alkanes. Now because transition state has a very limited radical character, therefore, the stability of radical does not play any part in determining whether the product will be tertiary or primary. So therefore, in chlorination reaction, uh, the tertiary product is not that much preferred over the secondary or primary. On the other hand, the bromination reaction is endothermic. So therefore, according to Hammond's postulate, in endothermic reactions, the transition state resembles more like product. And in case of a bromination reaction, the products are free radicals. Therefore, the transition state resembles more like free radicals. Hence, the transition state has a significant radical character. So therefore, in bromination reaction, regioselectivity is greatly influenced by the radical stability, and we know that tertiary radicals are more stable. Hence, the tertiary radicals will be formed more preferentially, and therefore it explains why the tertiary product is more favored in bromination reaction.